We're going to talk about the frequency of vibration and the period for the two simple harmonic oscillators we've seen from Chapter 10, the simple pendulum and the mass spring system. We're going to start just with the mass spring system in this video. I'm going to bring in some equations that we already know and have used. From the second law, the sum of the forces acting on an object is equal to the rate and change of the quantity of motion, or ma. We had also defined in rotational motion that the angular velocity omega was equal to the change in theta, the change in the angular displacement, divided by the change in time. My gosh. Okay, we're going to talk about the frequency of vibration and the periods for the two simple harmonic oscillators we introduced in Chapter 10. One, the mass spring system, and then two, in another video, we'll look at the simple pendulum. We'll start just with the mass spring system in this one. We'll use some equations that we've already encountered. One is the second law equation that I have in the top left. The sum of the forces acting on an object is equal to its rate and change of quantity of motion, and that's ma. So F equals ma is with us up there. We also have defined omega in rotational motion as the change in the angle divided by the change in the time. So we said theta was analogous to the displacement delta x, and therefore its rate and change was analogous to omega and the velocity in linear kinematics. Now if we have the change in theta, the change in theta is 2 pi radians. That's what it takes to complete one cycle. 2 pi radians is one cycle, one complete back and forth movement. And the amount of time it takes to complete one back and forth movement, or one cycle, we call the period t. Now we had already discussed, even in circular motion, that the period t, the time it takes to complete one revolution or one cycle, is equal to frequency to the negative 1, or 1 over the frequency f, where frequency is measured in cycles per second, how many cycles every second. So you can see from here, we can substitute this value in for t, and we'll get for omega 2 pi f, or 2 pi times the frequency. And this is what we called, and named in Chapter 10, as our angular frequency. We also had some new values where we could describe the position, the velocity, and the acceleration of a simple harmonic oscillator. We showed from the reference circle how we can find the position x in a simple harmonic oscillator by multiplying the amplitude a, which was representing our radius in that reference circle, times the cosine of theta, the angle at which described its position on the reference circle, and that angle theta was also equal to omega t. And just in the same way that distance is equal to speed times time, so we had theta, an angular displacement, equal to omega t. So we said we could find the position x by finding a cosine omega t. We were able to then show velocity. The velocity of the harmonic oscillator, using our reference circle, we found was negative a minus the amplitude pointed in the opposite direction, omega times the sine of theta, which again was the sine of omega t. We also then found the acceleration. The acceleration for that object that is oscillating with simple harmonic motion was negative a, again for amplitude, omega squared, cosine omega t. So here we have in blue these new equations for position, velocity, and acceleration. And we also showed what the maximum amounts of velocity and acceleration would be when this value here, sine omega t for the velocity, we found out what that would be at a maximum. When that equals 1, we get a maximum velocity, and when cosine omega t equals 1, we get a maximum acceleration. We can use these in conjunction with the equations on the left to determine a relationship between the frequency of vibration and the mass and the spring constant. We had introduced Hooke's law, which told us that the restoring force of the spring, or this could apply to a rubber band too, but this is talking about an ideal spring. The spring force is equal to minus kx. Remember, the minus sign is in there to remind us of an opposite displacement, a displacement that's in the opposite direction as the applied force, or the spring force. Okay? So if we go back to our F equals ma, law 2, and we write it down here, the sum of the forces equals m times acceleration a. We can say, hey, we just found out what the acceleration for the simple harmonic oscillator was. There it is up there. So we have the sum of the forces equals m times negative amplitude omega squared cosine omega t. We also have a value for what the force, the restoring force in the spring should be. Okay? We have this value for what the force should be, given by Hooke's law. So we can substitute this value in, underlined in green, for our value of force. Let's write it out. Minus kx equals m. Now this is not, I'm going to put my parentheses in here that I forgot to include. All of this in parentheses represents my acceleration. Keep my parentheses there so I know I'm not subtracting. Negative amplitude omega squared cosine omega t. And where else can we go with this? Well, now I have this x, my displacement of the spring. The ideal spring has been displaced with a force, a restoring force equivalent to kx, but in the opposite direction. Let's go see what my position of the oscillator is given by. There it is, a cosine omega t. So I have minus k times a cosine omega t equals what I have just above m times negative amplitude omega squared cosine omega t. Now we have an omega in there that we can solve for. We're going to look at solving for this omega, which we said before. Notice up on the left, our omega here, the angular frequency, has a relationship to the period big T. It also has a relationship to the frequency f. So we can solve for that omega. We can talk about the frequency and period of our harmonic oscillator. So let's see how we can solve for omega. I have negative k times a cosine omega t, and I have m on the other side times negative a omega squared cosine omega t. Let's see if I can work around this a little bit. I have an m that needs to come to the other side. I have a cosine omega t, and I have an a cosine omega t. So if I solve for omega squared, we'll start with solving just for omega squared. I have minus k a cosine omega t divided by minus m a cosine omega t. What am I left with? Omega squared on the other side. You can see my cosine omega t will go away, my amplitude a will go away, and my minus 1 will go away. I'm left with k, the spring constant, divided by the mass m equals omega squared. Let's take the square root of both sides. If the square root of k over m is giving me my angular frequency omega, let's box that one. Now how can I relate this to period? We can scroll back up and remind ourselves that omega, over there on the left in the green, is equal to 2 pi f, or 2 pi over t. So this is also equal to 2 pi f. It's also equal to 2 pi over t. Let's solve that for t. I have 2 pi divided by big T, the period, equals square root k, spring constant divided by mass m. Let's square both sides. 4 pi squared over t squared equals k over m. Now let's solve for t. T squared equals 4 pi squared m over k. I can pretty it up a little bit. And then I'll take the square root. Period t equals 2 pi times the square root m over k. Let's clean up that last k. Box that one. So we have, for the period of a mass spring system that's in simple harmonic motion, we have the period given by big T equal to 2 pi times the square root of m over k. We can also say what its angular frequency is. That's here with our omega. The angular frequency is the square root of k over m. This is the relationship that allows me to go and find big T for the period of the mass spring system. In order to get these values, we started with our Newton's law 2, F equals ma. We used our values for position in simple harmonic motion and acceleration that we derived from the unit circle. And we incorporated our knowledge from rotational kinematics of omega to show that omega is equal to 2 pi f and has a relationship to big T period. Lastly, we brought in what we experimented with by the stairs with the large spring, Hooke's law. And with those powers combined, there we found omega square root of k over m, and the period of the mass spring system, 2 pi times the square root m over k.